Hello everyone. So today we are going to study about the correlation between the time and the frequency response for a second order system. So let's take a typical second order system. Gs equals to omega n square divided by s square plus 2 psi omega n s plus omega n square, where omega n is natural frequency and xi is damping ratio. Okay, and S is Laplace operator. Okay, so let me draw a typical second order frequency response of a typical second order system, omega, and let's say this is a magnitude. Magnitude is j omega, like this. If Gs is a transfer function, then the frequency response of this system can be calculated by substituting value of S is equals to j omega, and it will give omega n square divided by j omega whole square plus 2 psi omega n j omega plus omega n square. Okay, so we can rewrite this equation in this form: 1 divided by minus omega by omega n whole square plus 2 psi omega n by omega n plus 1. Okay, and this is also come with the imaginary part j. So if we calculate the magnitude of the system, this equation, then the magnitude j omega will be equals to 1 divided by square root of the square of the real part, which is 1 plus omega by omega n whole square. This is square, this is square, this is minus, plus square of this term, which will be the 4 j square omega by omega n whole square. Okay, so let us simplify this equation in terms of normalized frequency. So let me write omega by omega small n equals to omega capital N, and this is nothing but it is a normalized frequency. Okay, normalized frequency. So let's look at here. Now the typical response of a second order system is like this. Okay, there are some properties of this frequency response. The first is this peak and the frequency at which this peak is generated. This peak is called resonant peak, and it is noted by MR, and the frequency at which the peak is generated is called resonant frequency. Okay, and another thing in this frequency response is that the 3 dB frequency, as we know that this response, this value is nothing but the magnitude of magnitude of the transfer function at frequency equals to 0. This is a 0 frequency. So let me calculate what is this actual value in the case of the standard second order transfer function. So magnitude of Gj0 is equals to, when we substitute omega equals to 0, we will have magnitude 1. Similarly, when the magnitude of Gj infinity, when the frequency is infinity, then the magnitude will be equals to 0. So this magnitude at frequency equals to 0 is 1. And for calculating the bandwidth, we know that we consider mainly the 3 dB frequency. And the 3 dB generally referred as when your magnitude fall down to a 70.7% of its initial value, or in terms of this magnitude Gj0 divided by square root of 2. This can also be represented like this. Omega B is called bandwidth. Okay, so there are three things that we have to measure. The one is the MR. This is the resonant peak. One, we have to calculate the frequency, resonant frequency, and third, we have to calculate the bandwidth of the system. And we will try to correlate this value with the time domain parameters. Like if is it have any relation with the time domain parameter or not? Okay, so how to calculate it? Now we will first look at this point. Here we see that this is the maximum peak. So for calculating any maximum or minimum value, we generally take a help of the calculus. So with the help of calculus, we simply derivate this term, and at this point we know that since it is a stationary point in this graph, so d by d omega of g j omega should be equals to 0 if it is a stationary point. So we will go through this procedure and look at it. This is the value of g j omega. So we will calculate d by d omega of g j omega equals to, solving this equation, differentiating this equation, we will have denominator which is the square of the actual value. It can be written as 1 minus, now I will write omega n instead of omega by omega n. I have already defined omega by omega n equals to omega capital N, which is a normalized frequency, square, plus 4 c square omega n, this is also capital N square. Okay, so and the upside and at the top we will have this expression 0 minus 1 by 2 of 1 minus omega n square whole square plus 4 xi square omega n square multiplied by differentiation of this part. Okay, so also it will have minus 1 by 2 square root, because here it was a square root, so when we differentiate this term we will have 1 by 2 outside, and we will have minus 1 by 2 this power, and we will also differentiate inside of the part, and inside part will be like 1 minus omega n square into minus 2 omega n, okay, and plus 8 chi square omega n. So this is the whole expression. So you can see here there are two separated part, this part and this part. Okay, so this should be equals to 0. We know that for the for satisfying the maximum principle. So equating this equals to 0, we will have this expression which is minus 2 1 minus omega n square into minus 2 omega n plus 8 psi square omega n equals to 0. All other terms will be equals to 0, and solving this equation we will have the value of omega n equals to square root of 1 minus 2 xi square like this. And since we know that omega n equals to omega by omega small n natural frequency, since this is a resonant frequency, at this frequency the magnitude of your system is maximum, so we will represent it by, instead of omega we will represent it by the omega r. So the expression of the omega r, which is nothing but a resonant frequency, equals to omega n square root of 1 minus 2 xi square. So this is your expression for the resonant frequency. Now since we have resonant frequency, now we can also measure, we can now easily measure the value of the resonant peak. How we can easily measure? See, look at the equation of G omega. If we substitute the value of omega equals to omega r, we will able to find out the expression of the resonant peak. Okay, now mr can be written as mr equals to magnitude of g j omega at omega equals to omega r, and the expression of the omega r is here. So substituting this value, I will not go into a detailed calculation, you do it by yourself. The expression you will find out for the resonant peak, it will become like this: 2 xi square root of 1 minus xi square, and this is we call a resonant peak. Let me write here like this: mr, the resonant peak, is equals to 1 divided by 2 times of damping ratio divided by 1 square root of 1 minus damping square of the damping ratio. Okay, so this is your expression, second expression, like this. Now since we all have the omega r we have and the resonant peak we have, now we have a third objective we have left, which is a third point was, what was the third point? It is bandwidth of the system. We can measure the bandwidth of a system if we are able to measure the frequency at which the magnitude of the system fall down to its 70.7% of the value, or we can say in terms of dB, it is a 3 dB of magnitude, or we can also represent in terms of GJ0 divided by square root of 2. So using this expression, for the bandwidth calculation, we can simply use this expression G j omega when divided square root of 2 when omega equals to 0. This is your 3 dB magnitude. This is 3 dB magnitude. It should be equals to your actual magnitude j omega b, when the frequency of your system is at this point, this 3D at the 3 dB magnitude, the frequency of the system is omega b. So we can use this expression and simply solve this expression. Solve with this expression, we know that g j0 magnitude of it equals to 1. So we can write 1 by square root of 2 equals to, using the expression magnitude of g j omega, this is the expression of the g j omega. By using this expression, simply substituting value of omega equals to omega v, we can simply write it 1 divided by square root of 1 minus omega b1 square plus 4 xi square omega b1 square. Okay, here omega b1 I have represented equals to omega b divided by omega n, because here in this expression omega by omega n square was there, so instead of omega I have written here omega b by omega n, and this whole quantity I have represented in terms of omega b1. So this is your expression. By solving this expression we will have this kind of fourth order equation, omega b1 square minus 2 1 minus 2 xi square omega b square minus 1 equals to 0. Solving this equation, omega b square will be equals to 2 1 minus 2 xi square plus minus square root of 4 1 minus 2 xi square whole square plus 4 divided by 2. 2 can be cancelled out from here. So we will have final expression for omega b1 equals to omega b divided by omega n equals to square root of 1 minus 2 xi square plus square of, we have neglected the negative sign here, 1 minus 2 xi square plus 1. This is your expression, and the final expression can be written here like omega b equals to omega n, which is bandwidth, omega n square root of 1 minus 2 xi square plus 1 minus 2 xi square whole square plus 1. Okay, so this is a complete square root. So this is your final expression for the bandwidth. Okay, now we have calculated three main parameters for the frequency domain analysis. In the frequency response, we have calculated the resonant peak, resonant frequency, and the bandwidth. Please note that this peak, let me rewrite it here again. Please note that this peak in the frequency domain, if it is omega, and this is magnitude of g omega, will only exist when your damping ratio is less than 0.707 and greater than 0. So this all expression will be valid for this damping ratio condition. Okay, if we look at here, this peak will also only exist when we have damping ratio in this range. If your damping ratio is greater than 0.707, you will be having a flatter response like this. So no peak will exist in the frequency domain. Similarly, if we correlate this frequency domain analysis with a time domain response, when we have a damping ratio within this range, we will have this kind of response, and we will have the MAMP, which is the maximum overshoot, exist. Maximum overshoot. Okay. So we can say that this is in time domain, this is magnitude, let's say write it into y. This is in time domain. We can say that if a maximum overshoot MP, which has an expression of e to the power minus xi divided by square root of 1 minus xi square pi, if it exists in the time domain, then we can say that there will be a equivalent peak that will exist into a frequency domain, which has an expression of MR, we call it in frequency domain, we call it in the resonant peak. Then MR will exist, and the expression of the MR will be 1 upon 2 xi 1 minus xi square. Okay, it will be exist at the frequency we call it resonant frequency omega r, and the expression of the omega r is omega n square root of 1 minus 2 psi square, and the bandwidth of the system will be omega b will be equals to so correlation. We have studied that if a maximum overshoot exists into a time domain system, then there will be a peak also exists into a frequency domain. The peak will be called as resonant peak. It will have a frequency of it will exist at the frequency of omega r, which is the resonant frequency, and will have a bandwidth of omega b. Here it will be omega n, omega n will also there. So omega n into omega b. Let me rewrite it. Omega n this. Okay, thank you. This is your final expression.